That's an interesting little project uh, that kind of came up that these guys at Diamondback, we've known about this for a while, but they tried to push something out and it kind of got messed up, and now they're coming back and asking for help. But let me just kind of roll through this real quick here and then paint the picture of what the problem is for you. So this is a presentation that I put together from, I guess it was last October, as part of like a training circuit for P&P, right? To get them up to speed on this stuff. Now, I don't know if like Falan had slides like this, if you got this from Chula or about these things, but as I've got here, like, petrophysics is physics, right? And that's what this is. This presentation is designed for, is to give you the idea of what the physics are on the tool, how it's being designed, and what it's measuring and all that stuff. So, long story short, right? The project that we got is based off of neutron tool data, if you couldn't guess. So I'll step through this really quickly here, but I just want to give you an idea of what the problem is. So this neutron stuff, a long time ago, the tool people, these physicists that were hired by the oil companies to develop these sort of things, right? They understood that you could use neutrons as a source of information to bombard a rock with, full of fluids, and that the neutrons would interact with the fluids a certain way, and that you could measure the interaction rate. So it's like, in chemistry we have reaction rates, in physics we have reaction rates. It's something going on. There's particles, there's a certain count rate of particles, right? And this stuff here is elastic scattering of neutrons mostly. So there's a couple of things that really need to kind of point out here. One is that the chemical source that's in the tool, okay, it's usually americium beryllium, and this source spits out high energy neutrons. Okay, the neutrons bounce around, they interact with different nuclei in the rock. The detectors on the tool, okay, these detectors are semiconductors, essentially, in a lot of cases, or they're fancy neutron detectors which have helium, a special isotope of helium, that when that helium interacts with the neutron, it's able to kind of get a reaction that produces something that can then go to a scintillation detector. But ultimately, everything winds up in a scintillation detector, semiconductor, that kind of operates off of photoelectric effect physics, right? So like an electron hits it, and that causes a current, and the current's got a certain amount of amplitude to it, right? And it's got a frequency, like how many counts am I seeing, type of thing, right? We're trying to convert gamma rays or whatever into some sort of, something that we can see. We do that with photoelectric electricity type stuff, right? Anyways, point is, there's two different things that we can measure with a neutron tool. We can measure neutrons, or we can measure gamma rays. Okay, and the newer tools measure neutrons. The older tools measure gamma rays, and that's sort of the reason that we've got a problem. Okay, this is how this all works, right? You got like a neutron that comes in, hits a nucleus, it scatters. Okay, elastic scattering. And when it scatters, it loses a little bit of energy. Right? This is not anything really that complicated. It's like classical mechanics, physics, you know. After enough collisions, the neutron loses that it's called something different, right? So like you've got fast neutrons that come out of this source, this beryllium source. Once they've collided so many times, then they become a slow neutron, right? Then they become like an epithermal neutron, which means it's almost thermal. And then they become a thermal neutron. And that's when you can have neutron capture. Once it releases, or once it releases enough energy that it gets down to the thermal stage, this picture on the bottom down here is what happens. So that neutron's, it's so low energy now, right? Instead of elastically scattering, like it hits a nucleus and it just becomes part of the nucleus now. It's like goes right inside of there, right? And when that happens, the whole nucleus becomes excited, and in order to sort of re-equilibrate itself down to a ground state, it releases this prompt gamma ray. So the neutron tool thing is either I'm measuring how many of the neutrons there are and doing spectral analysis to see what the energy levels are, like how many epithermal, how many thermal do I have? That tells me how many times they've collided with something, and the something that they collide with that slows them down, they lose energy from, is hydrogen. And hydrogen is in water, and hydrogen is in hydrocarbon. So they use this tool. It's actually a hydrogen index tool is what they call it. It's measuring the amount of hydrogen down hole. Then that's correlated to porosity, right? Because there's not much hydrogen in matrix minerals. But two different mechanisms. Do I measure the neutrons, or do I measure the gamma rays that come after the neutron is captured, right? So there's a bunch of other stuff here, but just to give you an idea, right? There's like these different energy windows: fast neutrons, epithermal neutrons, and then thermal neutrons, very low energy. Like there's a chemical source way up here, right? Simple stuff. And how these energy losses, number of collisions, again, like how many times does that neutron need to hit a hydrogen atom? But this is, I think, discuss this stuff, right? This is the neutron needs to be converted to an electrical signal that we can measure with a computer and all that. And to do that, they use these helium detectors. So you've got this helium-3, and this is a chemical reaction, right? Helium-3 plus a neutron is equal to blah, 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 right? And they ionize the gas and create a voltage, right? And that ends up in the pulse height is proportional. So you kind of get usually two detectors. This is getting down more on the stuff that I was doing before, and I can hand some of this code over to you also. I wrote a whole bunch of Python stuff using OpenMC, which is a nuclear physics simulator, Monte Carlo simulator, where you can actually do this stuff. So I'll show you some slides, right? Like these plots, you create a rock. You just tell the simulator this is 100% limestone, 0% porosity, and you let the simulation run, and it actually captures all these neutrons that it sees, and then you can calculate this stuff, right? There's chart books that have all these things and calibrations, and this is just a bunch of other crap in here. But like here's the simulation work, right? So, I was messing around with different particle counts and the uncertainty, because we know what the answer is, right? We gave it the answer. We said this is 5% porosity limestone. So, but this is what the simulation is actually doing, right? So like you've got the two detectors here in the blue squares. And then you've got the source down here at the red dot. And so you've got this flux of neutrons that are coming out from that source, interacting, losing energy, right? And then the detectors are counting how many neutrons are coming in at different energy windows. You're doing some spectral decomp. And this is kind of what these things, intermediate, fast, epithermal, and thermal, what these clouds look like, you know, from all these particle paths that have been simulated, you know. So again, some animations and things. Energy evolution. Anyway, here's the problem that we have. So Diamondback has got 100,000 gamma ray neutron logs. 100,000. Right? That they want with. And I think Sam 30,000 of these are old neutron logs. So the new ones, like I've got on this slide, the new ones, they're compensated neutron. So these tools are measuring the, and the output from this thing is porosity units. That's what you get, right? The older tools, these 30,000, are either like sidewall neutron tools, which instead of giving porosity now, it's just giving you an epithermal count rate. So it's like proportional, because epithermal count rate, you know, is what it is. And then you've got these things that are called gamma ray neutron tools, which are in these API, neutron API units. So like, you know, you've got gamma ray API units for normal gamma ray tool. These are also gamma rays, but they call them neutron API units. And this is where the problem lies. So, you know, how do we deal with this data? You know, there's some charts. We can do some additional simulation work to try to figure out what the correlations are. You know, they may not be, you know, for the count rate of neutrons, we already know we could do a long to short ratio, right? And we can plot it right here. So the short to long thermal ratio follows this sort of lazy parabola, right? It's not linear, but some quadratic function, right, that you've got here, or polynomial. But this is to neutron, and it's also to the ratio. So we kind of need to figure out, there's a lot of chart books and stuff out here too we can use. But the problem they've got is that, you know, because of this, it's not like, you know, the guy that's doing this in the geologic software is just trying to apply a single formula, like high neutron API equals high porosity or something, right? And that's not working. It's broken miserably. And we know that it could be either way, depending on what we're looking at, right? If it's the prompt gamma rays that are coming from the capture process, that's directly proportional to thermal neutrons, which means that's proportional to porosity. If it's fast neutron count rate that we're looking at, fast neutrons means there's not any collision. There's a lot of fast neutrons out there, right? And if that's the case, high count rate means low porosity, right? So like we've got both ways where it could be high count rate of gamma rays is equal to high porosity, or high count rate of fast neutrons could be equal to low porosity, right? So the biggest problem here, yeah, there's a lot going on, and the biggest problem here is the size of the data set. So that's why I'm thinking Python may be the way to go for this one, because we can try loading it. We can't use IP. IP is not going to work with 30,000 wells, right? We could try using the software that I've written, the PetroRes Studio thing. That may be able to handle this problem. That's what it was designed for. And then alternatively, we could try Python, because it probably gives us a little bit more flexibility in how we can deal with the data. But we're going to need TOPS, right? We're going to need, in order to understand what the data is. Like, it's not like every single one of these wells is going to tell us this is a sidewall neutron, this is a gamma ray neutron. We don't know. All we have is a neutron curve. We don't know anything about it other than the units are in counts. Are they gamma ray counts? Are they neutron counts? We don't know. Right? Maybe we're lucky and it tells us that we have API units, so we know that it's gamma ray. But and then as I noted on this slide, right, these things are very sensitive to environmental effects. So that, that's what that's telling you, is that's kind of screaming machine learning normalization. So, like what we'll have to do is kind of make a map, essentially, of kind of look at some of these things and use statistical levers to, if I've got 1,000 wells in an area, and the units vary a certain way, and some of the wells are just different. Why are they different? Right? Like, if everybody else has got values from 5 to 10,000, but these guys are 100,000, something's wrong, right? How do we deal with that? So this is like the ultimate clusterfuck data science problem that you will see over and over again in your career, where you've got these gigantic data sets, and to do it correctly, right, would require a whole team of people and like 10 years of time to fix it all. But we need to do it in a day, type of thing, So we got to do a better job than what the geologist did, which is, he just took the count rates and just divided it by 1,000 or something and said that's my porosity. And that didn't work. So I think we can do a better job than that, but it's going to be the first part of all of this. I think the easiest way to deal with it is to kind of do what we've been doing with some of that software we got in IP and stuff, just to cull the data set down, right? And say, out of all these 30,000 wells, these ones are bad ones. Put them aside and come back to those later, because there's something wrong with them. But definitely going to be a challenge. So I'll continue to talk to Corey. I'll be out there next week, and if I can, I'll try to set up a meeting or something, and I'll try to get it. If I have to, I'll just call you on my phone and just let you listen to, if we can't get a conference room set up or whatever. But we'll have some conversations around this. I'll probably meet with Ben as well, the geologist that tried to do this on his own, and see what we can do. But everything else going all right? I could barely hear you. Wow. Anyhow, um, we'll yeah, I'll loop you in next week also for we'll discuss this core facies thing some more. I'll get some meetings set up in the morning so it's not too late for you, right? And I'll get Michael and Corey and some guys and I showed Doug the work that he said it was really, really great. So and I don't know if I told you, but if you look at can you pull that thing up and share your screen really quickly, that PDF that you made? And oh, that's okay. That's okay. Well, anyways, I sent you a screenshot on Tuesday of the geosteering, right? And all of those stages, 13 through 18, that had the low ISIPs and everything, that's in a zone that's limestone. So normally they are in a dolomite reservoir, but for whatever reason, those stages they cut into a limestone and they have it on the mud log. It's like 100% lime, and that's where everything went. So they did cut a different lithology there. It went from dolomite to limestone. Yeah, well, I kind of figured that's what it was going to be. Is that something changed, reservoir properties, something happened that um, caused all those changes in the ISIPs. Because otherwise, why it doesn't make sense. So yeah, for sure, that's what happened. Is there's that big limestone section, and we don't have it's the well. By the way, it just they've been flowing it back at, like, I don't even know, 3,500 barrels a day or something, or um naturally. No, it's just flowing the surface on its own, and it's been cutting oil now. Like, I think when I was in the office on Tuesday, they had some pictures of jars and stuff that they're taking off the separators of oil. So they're gonna continue to flow back for a while, and I think then they're gonna kill it, and they're gonna put a production string in there with an ESP, and then they'll start to pump it off, right? But it looks like it's cutting oil, and the fact that it was flowing on its own at 3,500 barrels a day with, that means that we got some connectivity down there. So it sounds like it's been a successful frac job. So everybody's pretty happy with the way that it turned out. But we'll see what the final rates look like. I'm still concerned that we didn't put enough proppant down hole, and we're not going to see a lot of rates. But who knows? If it's flowing the water, it should clean up. Relative perm should clean up, and it should start to flow quite a bit of total liquid, regardless, right? So it's also a half to 1 millidarcy reservoir. So you just drilled a 1.5 kilometer long well into this is like a lot of good rock that's been contacted, right? Okay. I just wanted to let you know about this neutron thing. This will be an interesting project, but in the meantime, well, did you ever get that laptop from Game? Did she send it? She, she didn't send it to you? Yeah. I just sent her a message asking if she can send it to you. Because that laptop, the guys at the gang software development were using it to write software, but it's got IP installed on it already. So the should be able just to log in and go. You just have to set up your Microsoft account. Oh, you're in Bangkok? Okay, yeah. I just sent her a message, so she's probably sleeping or something. But if you're hanging around, yeah, we should have done this like earlier today so that you could have it already. But if you don't, if you want to go home or whatever, we could just have her mail it to you or whatever. But um, anyway, all right. Well, enjoy the weekend, and next Tuesday we'll be in the Diamondback offices, and we'll set some meetings up and to you. Sound good? Okay. All right, cool. Well, we'll talk to you later then. Go get some sleep.